All right, so I'm gonna click record, and here we go. Okay, so we're gonna start with chapter 6. So you guys know the first reaction is going to be hydrohalogenation. So, you know, don't write name, but maybe write hydrohalogenation. So hydrohalogenation, okay? And maybe I'll say of alkenes, okay? Because we know we have an alkyne version, okay? So I write hydrohalogenation of alkenes, okay? So our first example, let's just do an example like this, okay? Subjecting it to H, maybe let's just do HX, just for simplicity purposes. And let's draw our mechanistic arrows. So we know our nucleophile is the pi bond for reasons we've discussed. It grabs the electron deficient proton. Why did we know it was electron deficient? Well, there's a localized dipole moment towards the halogen, making that partially positive. So the nucleophile with electrons, which is negative, likes the positive thing. We exceed the octet, and we generate what is a carbocation intermediate, okay? So this is a secondary carbocation intermediate, so maybe write carbocation, okay? And then X minus is gonna be your halogen. It likes the positive thing. So then you generate the halogen, maybe put a star to say that it's chiral, and I'm just gonna write in parentheses racemic. Remember that that means we went from, and I can even say maybe sp2 to sp3. Okay, so don't forget that we typically have a chirality situation that we have to deal with, okay? So was this regioselective? Absolutely, it was regioselective. So maybe I'll say yes or Y, okay? It's regioselective in the sense that it follows Markovnikov's rule, okay? We're forming the more substituted position. And is it stereospecific by any means? No, it's not stereospecific because we're not exclusively getting, you know, one specific arrangement of atoms. We get both the wedge and the dash orientation. So yes, this is just an example of regioselective, okay? And it's not stereospecific, okay? Everyone good? Let's keep moving, okay? So the next question is, I'm sorry, not next question, but we're gonna do reaction 2 over here. And this is going to be acid-catalyzed hydration, okay? And guys, if you see your peers have some questions in the chat box and you're capable of answering them, by all means, please answer them so that I can just keep going like throughout this and not stop, okay? So acid-catalyzed hydration, okay, of alkenes. Okay, so we're here. Let's do an example of that. Okay, so let's take maybe this. Okay, am I running out of ink? Okay, and let's subject it to, remember this is H2O, and let's just do HCl, let's just do catalyst. Okay, so we're here. And essentially we knew that that was like hydronium reacting with this. Okay, so the mechanistic arrows would be the nucleophilic pi bond grabbing a proton, and then the electron staying on the oxygen. And that makes sense because we have a more electronegative atom in that bond, and it's going to be retained on the oxygen over the hydrogen. Okay, so the result again is this carbocation intermediate, which follows Markovnikov's rule. So maybe I'll write carbocation. Okay, and then the resulting step is we have water. Okay, water, and water, one of those lone pairs, is just going to come in and attack that sp2 center. So we get, you know, this water group attached, and we're one step away. And remember, we always say assume excess reagent. Okay, so we're going to assume that we have more water hanging out. Okay, and one of those lone pairs is just going to grab a proton, synthesizing that alcohol. Okay, and here there's typically we could get a chiral. Here, let me make it chiral. Let me just add another group over there. Okay, and I'll make it chiral. Again, the same sp2 to sp3 situation we have to deal with, okay? So again, this is this regio selective? And absolutely, it's regio selective because we're forming a, you know, a carbocation on the more substituted position. But am I stereospecific? Did I get exclusively one type of, you know, product? And the answer is no, I did not, okay? So it's just regio selective, which is good, okay? Are you guys liking this activity? We're doing the reactions really quickly, but I just thought this would be a good idea. Okay, good, awesome. Okay, let's keep going. So after this reaction, we have a different version of that one, okay? So this one is gonna still be called, instead of acid-catalyzed hydration, let's call it acid-catalyzed ether synthesis. That's what I call it, acid-catalyzed ether synthesis. Okay, and we don't have to say of alkenes because this is the only one we know. So acid-catalyzed ether synthesis. Okay, let's do an example of that. Okay, so let's just take the exact same molecule maybe we had, okay, before, something like that. And remember, this isn't water this time, it's an alcohol. So I'm just gonna say methanol, you know, it could be any alcohol, it could be ethanol, propanol, other branched alcohols. But we have methanol, and just in this example, and still that acid catalyst. So maybe I'll write that. Okay, so we knew that what our main reagent is going to be, instead of hydronium like it was up here, the result is going to be protonated alcohol. So it just looks like this. Okay, and the same mechanistic steps as we saw up here are going to happen down here. So the nucleophilic pi bond is going to grab a proton. Okay, we get a structure where we have a secondary carbocation. Okay, so again, I'll just write carbocation under here, carbocation, because that's the main intermediate. And then you have just the alcohol, okay, so H3COH, okay? And then the lone pair on the alcohol is just gonna come and form a bond, so that sp2 center. We get, this now substituent that looks like almost an ether. Remember, we assume excess reagent, so it's nice to have this extra methanol hanging out to remove that final proton, okay? And we synthesized the ether. Okay, again, I'll put a star to indicate that this would be a racemic. Okay, maybe I'll write that. I didn't write that above, let me just fix that up here, also racemic. Okay, and now let's ask ourselves our questions. Okay, was this regioselective? Okay, of course it was regioselective. It was the exact same one that we saw above. Was it stereospecific? No. Okay, we don't get exclusively one enantiomer or one diastereomer. We get, both. Okay, how are we feeling? Good? Awesome. Okay, let's keep going. So the next one is going to be halogenation of alkenes. Okay, so we're here. Halogenation of alkenes. Okay, so let's do another example of this. So let me think of a structure. Okay, so example, let's do, I don't have a lot of space, so I'm gonna do an easy example. Okay, no, the last one was not stereospecific if you're asking for that, no. Okay, so let's just do this example and we're gonna subject it to, Br2. And it could be any halogen, it could be X2, any Cl2, whatever. And I'm gonna pick an inert solvent, and specifically, let me just pick CH2Cl2. And I'm just gonna write, remember that was the DCM example. This could have been any other halogen, so maybe I'll just write up here, it's really X2, okay, so to indicate any halogen. And then this one could have been or chloroform, so CHCl3. So that's another inert solvent. Just trying to give you some information. This was, maybe I'll write like just above in purple, like this was a concerted mechanism. This was the first concerted mechanism that we saw, okay? And let's just kind of draw this out. So essentially we have bromine, diatomic bromine hanging out. We rationalize that we had a nucleophilic pi bond grabbing this bromine. We exceed the octet because of that. But remember, I said, and I'll draw it here, we have a partial positive that slightly develops. Okay, that's what that delta positive means, okay? A partial positive is we're taking the electrons away from this carbon, forming a bond to the bromine, but in doing so, you remove carbons from this, you remove electrons from this carbon, which makes it deficient. So another lone pair on that halogen comes back down, that's the concerted, the cyclic part of that, and we form this bridge, okay? So the resulting, structure would be something that looks like this. Okay. And this is going to be the only, intermediate we're getting, because the other one would be meso. So I'm just going to write meso under here. This is the, remember, this is the holonium, and I'll write this, holonium bridged intermediate. Okay, and I'll write ent. Okay, holonium bridged intermediate. Okay, and then remember that we had generated bromide anion from that first step. And then this is now my nucleophile that's going to do anti-addition. And remember, maybe I'll just write right here, sterics, so that you'll remember sterics. That was the steric argument, where because we're limited on the front face, that's the wedges, we could only come in and attack from the back face. So this incoming bromide anion is actually a dash, not a wedge. And then since we exceed the octet at this carbon right here, we have to share this bond breaking. Okay, so the resulting step is going to be something that looks like this. The bromine coming in on a dash and the bromine coming on the wedge. And we don't have to show the other one because if we show the other one, it would be the exact same structure since this is a meso intermediate. Okay, so this is called anti-addition. Okay, so this is anti-addition, that was important. And you get this exclusive product. Okay, so what does this mean in terms of regio? Okay, and stereo. Okay, so do we think that this is a regioselective reaction? Yeah, 100% it's regioselective because we had a more, typically we have a more this is no difference here, they're both secondary, but typically we could have a more substituted side. And remember, we talked about why one side might be attacked more so than the other and how to do with those alternating resonance structures that we showed. So yes, this is definitely regioselective. Is this stereospecific? Well, 100% it's stereospecific. We have something called anti-addition. And remember where those two groups that came in are 180 degrees. So yes, this is an example, the first example where we had a both. Okay, so this is a both situation. Okay, right? And remember, it's concerted and there's a steric argument, and maybe I'll also say, typically it's the more substituted position. Remember all these things? More substituted position. Okay, so those are the key things I remember for halogenation. Okay, we're gonna keep going. Okay, so the next one is going to be Halohydrin synthesis. Okay, Halohydrin. Oh, let me check something. Sorry, guys. Oh, there's 24 people in the room. Oops. Sorry. Sorry to all you people coming in. I feel so bad. I didn't know you were on the waiting room. Oh, I'm so sorry. Okay. This is going to be on YouTube, so don't worry. You didn't miss much. We're just going over the reactions. Okay. Here we go. So the next one is halohydrin synthesis. Halohydrin synthesis. Okay. So let's do an example of that one. Okay. So let's just take this example maybe. Okay. And we're going to subject it to Br2. And remember, instead of what we had above, which was DCM and chloroform, any of those inert solvents, here we're going to see water being our main solvent. Okay, and water is actually going to be the better nucleophile in this situation, and we'll talk about that in a second. So essentially, if I want to show this reacting, we have Br and Br, okay? This is, again, another concerted mechanism. So pi bond grabs that bromine, okay? We exceed the octet at that bromine. We develop that partial positive that we saw above, so then this bond is going to come back, okay? So the exact same kind of first step. That was a partial positive for the delta. This is going to be concerted, so I'll just write that up top. Okay, and essentially the result of that step was this bridged intermediate, and I'm going to draw both. So remember, what I typically like to do is I keep it flat, I rotate it, and I draw it in this kind of planar depiction where the bridge can form above it. Okay, so this is the bridge above, and I'm going to draw it like this. Okay. And we could draw the one where it forms below, okay? So I like to do it like this. It's up to you guys. And I'm just drawing these substituents just so you can see the orientation that they're in. I know that's not chiral. I'm just drawing it just so you can see. All right, so what happens is now we have this question, we generated free bromide, okay? And we also have water. So we have free bromide and we have water hanging out. So the question, remember, was which one is the better one to come in and attack and open that bridge? And we said electronegativity was our rationale. So out of these two, maybe I'll just write here electronegativity, question mark. Do you guys remember? And I'll underline water. Water is less electronegative than this bromine. So that's why water is going to come in and attack than that bromine, okay? So essentially, let's show that. So water is here, okay? And this is that regioselected part where, you know, the water is going to attack the more substituted position because the alternating resonance structures, remember we can say, maybe I'll write, just trying to give you guys these little hints, resonance, okay? The resonance structures of this intermediate, resonance of the intermediate, shows that you know, more substituted side is the more stable side or the more electrophilic side that should be attacked. So let's kind of draw that. So this water comes in, attacks at that position. Okay, and then it exceeds the octet, so we break that carbon-bromine bond, okay? And essentially what we get is this trans arrangement. Remember I said that? This is the trans arrangement that we've been getting, okay? And it's trans with respect to the incoming water group and the bromine that was also in, okay? So I'm just gonna draw these methyl groups back the way that they were. Since they're not chiral, I'll just draw them as lines and leave that methyl. And then we're one step away, we assume excess reagent, okay? And it's going to deprotonate that last proton, and you synthesized the halohydrin, okay? And I'm not drawing obviously water reacts with the other intermediate as well to get the other enantiomer. So I'm just gonna, abbreviate this as like plus, other, okay? So this is a halohydrin. How is it a halohydrin? Well, we have a halogen and a hydrate, adjacent to one another, okay? So this is another example of anti-addition, okay, anti-addition. This is the halo, maybe I'll write halo here. Maybe I'll write the hydrin part down there, okay? And I think this is pretty much all you really need to remember for that halohydrin reaction. And there is a modified version, we've seen in one example where this wasn't water, this was an alcohol, okay? So that's okay. Instead of it being OH here, what do you think, what functional group forms here? Okay, if I replace this with an alcohol, what would be this group? Not an alcohol, but a ether. Great, ether. Yeah, do you all see that? Ether. Okay, I hope you see that. All right, so now back to those questions, regioselective and stereospecific. So regio, question mark, stereo, question mark. Okay, was this regiospecific? 100%, we're attacking the more substituted, side. Am I stereospecific? 100%, I also have anti-addition. So this is another example of them both being yes, okay? So this is both, all right? Both. All right, so that's halohydrin synthesis. So now we're going to move on. We're almost done with chapter 6, if you guys can believe it. So we have oxymercuration-demercuration now. Oxymercuration-demercuration. And there is a version for alkyne. So let's say of alkenes, okay, of alkenes. Okay. So there are 2 steps here. So let's just draw an example of that. This is the first time where we have 2 steps. Okay, so let's just draw this example, maybe. This is nice, okay? And we are going to show step 1, okay? And that is going to be this mercuric acetate intermediate, mercuric acetate reagent. We also have an inert solvent, THF. And then we also have our main, alcohol. That's our alcohol forming reagent, the water, okay? And then in step 2, all we had was that weird reduction step that we're gonna say you don't need to know until Orgo 2. So we don't know the mechanism for 2. So maybe I'll write here, mechanism, check. Mechanism, no. Remember, we don't need to know that, okay? So you guys know that. And essentially, this is another one of those concerted mechanisms. So maybe I'll just write concerted up top, okay? And remember, this is going to form another one of those bridge intermediates, but it's not one of these halonium. So we saw halonium up here. We saw halonium over here. Now we're going to see this mercuric acetate intermediate. So let's kind of just draw that step real quick. So ACO, HGOAC, that's kind of the structure you want to draw, okay? Then you want to draw this nucleophilic pi bond grabbing the mercury. You exceed the octet at mercury, so you have to break one of those acetates. And that same argument where this partial positive is forming down here, so then that mercury comes back and fixes that deficiency. Okay, so the resulting structure would be, again, I do the same flat and I rotate it, and then that's kind of how I draw these bridges, but up to you guys. So I'm going to draw that and that, HGOAC. And then there's also, I'm just going to write plus other. Okay, because I don't want to draw both, I'm running out of space. Plus the other one, from approaching from underneath. And, the main step here was the fact that water is the, the main alcohol forming, reagent. And that's going to attack, again, the more substituted position, okay? This is, again, the same logic, the resonance structures. And we exceed the octet at that carbon. We have to break this bridge open. And the product of step 1 is going to be something that looks like this, HGOAC. This is, positive. We have 2 methyl groups here, okay? And what we need to do is just take that excess water that we have hanging around and remove that final proton to synthesize this weird alcohol. Okay, and then remember that, so this is the, let me just write down here, product of step 1 okay? And then I'm running out of space, but you know, we can just say that sodium borohydride part removes, so I'm just gonna, this isn't a real arrow, I'm just gonna draw this purple arrow then. If you go here and crossing it out, okay? Remember that it's replacing this HGOAC thing with a hydrogen, okay? So essentially you get an alcohol that looks like this. Okay, you see that? So you just erase this and it becomes a methyl, okay? So this is your final alcohol, okay? So in terms of your main questions, is this a regioselective or a stereospecific reaction? Yeah, it's definitely both, again, okay? It's regiospecific in the sense that water has to, you know, attack the more substitute position, and stereospecific because look at this anti-addition. Even though you're not going to see that in the end product, there was definitely this anti-addition happening here with these bridge intermediates. So this is definitely an example of both. So regio, stereo, so yes and yes, okay? And remember the difference and the reason why we even have this reaction is because actually in the chat box, yes or no, does this reaction have possible rearrangements occurring? No, great, exactly. So that's the point to remember out of all points. So here, maybe like, I don't know, no carbocation, okay? That's really big. That's the main part of oxymercuration. The fact that we don't go through this carbocation intermediate, we go through this cyclic mercuric acetate intermediate. Okay, I know it's kind of small, but that's a cyclic mercuric acetate intermediate, okay? Okay, let's keep going. So we're gonna be on hydroboration now. Okay, so hydroboration, oxidation, and there's an alkyne example. Okay, so more people are coming in. Hydroboration oxidation of alkenes. Okay. I'm trying to just go as fast as I can, guys, working through these. Okay, another two-step reaction. So let's kind of use this example. Okay, so we're going to do that, and we're going to subject it to step 1, BH3, and we had another inert solvent, so here it's THF. Okay, and then in step 2, it was different. We had sodium hydroxide, and we also added hydrogen peroxide. Okay, so we have those. So essentially, you know, we again only know the mechanism for step 1. The mechanism for step 2 is not covered. So let's just kind of remind ourselves of that. You need to know the mechanism for that. Mechanism you don't need to know for that. Okay. So what we said is borane is this interesting reagent where we have a, you know, more substituted and a less substituted side. So let's kind of show that. So this is H kind of a line in here, and then maybe I'll just draw a big exaggerated line and write BH. 2, okay, let me BH2. And remember, maybe I'll just write this in parentheses, boron the moron. So it was the logic of remembering that boron is allowed to be electron deficient with only 6 valence. That's what boron, I mean, the boron only has the 3 hydrogen bonds, each 2 electrons. So that'd be 6 total valence, okay? So in terms of mechanistic step, oh, I need the pi bond. This nucleophilic pi bond is going to be able to attack that electron deficient boron, right? And then that, you know, is sufficient enough, it's stable, so we don't need to have 8 really valence electrons. So this boron hydrogen bond is going to break and come back. And remember, this is partially positive again. So that bond is going to break and come here and fix this. So again, this is another one of those concerted mechanisms, okay, concerted. Okay, and notice that we have these 2 fragments, the BH2, I call them fragments, okay, remember, these fragments. And we have the BH2, which aligns, this is the steric argument. So again, in purple, I'll just write a little thing to remind you, this is a steric argument. Wait a minute. Guys, 1 second. One second, sorry. Sorry, I'm just checking the election. I'm like really into it. Sorry, 1 second. Okay, all right, we're back. All right. So essentially we have, you know, this steric argument that we're doing here, okay? And, you know, we said that since this is a tiny molecule, both of those groups, the BH2 group is coming on and so is the H group all at once. So basically whatever stereochemistry the BH2 group is going to come in on, the H also has to agree with that. So that's why we had syn addition. Okay, so this is a different type. This is the first time we're seeing syn addition at this step. So I'm just going to draw this a little exaggerated. Okay, so essentially the H comes in on a dash, and then the BH2. I know there's no stereochem, but I just want to show it for all intents and purposes here. Okay, so this is my main result of step one. Okay, so product of step one. Okay, and then in step two, that hydroxide, you can imagine, is my nucleophile, and we know it's going to replace this, but we don't cover the mechanism. So you can just remember, you can draw, instead of, bonded BH2, you can essentially just say that, and this is the product of step two. So notice that this was anti-Markovnikov addition. So we had the alcohol added onto the opposite face. I mean, the allosterically hindered face. So in terms of regiochemistry, yes, there is it's regioselective, but this is anti-Markovnikov for the first time, okay? And also, in terms of stereochemistry, yes, this was syn addition. So yes, it was both as well. Okay, let's keep going. So the next question, I keep saying this. This one is dihydroxylation, okay? Dihydroxylation of alkenes. Okay. So this is the osmium tetroxide one, and this is another concerted step. Okay, so essentially, let's just take this example. Okay, we have this, and we're going to subject it to three main reagents. So osmium tetroxide. Okay, we have water. Remember, that's the hydrolysis step. And then we had hydrogen peroxide. And I said you don't need to know what hydrogen peroxide is doing in terms of the mechanism, but just be aware that hydrogen peroxide's role is to regenerate, your main osmium tetroxide reagent. Okay. Sorry, 1 second, guys. Just keep refreshing my computer. All right. And so here we are. So this is another concerted mechanism, another cyclic mechanism. So I'll just write concerted in the top. Concerted. We're almost done with chapter 6, guys. Okay, so essentially, let's just draw that down here. OS, and then you need to know this Lewis structure. Okay, and it's going to be the nucleophilic pi bond, okay, hitting this oxygen. Oops, let me draw this in red, sorry. It's nucleophilic pi bond, hitting that oxygen. One of those pi bonds in the carbonyl swiveling over to the osmium, and then that forces one of these pi bonds to come and hit that, again, deficiency. I'll just put partial positive so you remember. So the result of that is going to be this like huge bridged, cyclic. Okay, so this intermediate is a different thing, and we should know the name of this. So this is the cyclic osmate intermediate, and I'll write that below. This is cyclic osmate intermediate. Okay, so we have a couple intermediates we know. We have carbocations, halonium bridged, mercuric acetate bridges, and this is the cyclic osmate intermediate. Okay, lots of different crazy words. Okay, so we're here. And then essentially what we said was we don't need to know the mechanism beyond this point, but water is just going to do something called hydrolysis. Okay, and hydrolysis just means to cut with water. So I'm just going to draw a big line through here. Okay, that's what it's doing. And then the result is going to be 2 alcohols, syn addition. Okay, so this was, again, another type of syn addition. Okay. And this reaction, okay, if we're asking ourselves the question, is this regioselective, question mark, or is this stereospecific? Well, I didn't have a regioselectivity thing happening here at all. So no for regiochem. But for stereochem, yeah, we got syn addition, so yes, okay? So this is the first time where we had no for regio and yes for stereochem, okay? And of course, you can imagine this coming on a dash, but because it's a symmetrical molecule, it's meso, and there's no real difference there, okay? Sorry, 1 sec, guys. Okay, so that's dihydroxylation. Okay, so after that, we're going to do ozonolysis. So flip your paper over. Okay, so we are here. Okay, so we are reaction. Ozonolysis. Okay, and it's only for alkenes, so we don't have to draw anything else. Ozonolysis. Again, another mechanism that's not covered. Okay, so I'm just going to draw maybe this example. Okay, because I like these rings for these. Be prepared to have a ring question with this. And this is another 2 steps. So step 1 is ozone gas. And step 2 is dimethyl sulfide. So it's CH3, 2 with an S, and it's sometimes referred to as DMS. So I'll put that in parentheses, DMS. Okay, so again, we don't know the mechanism, so that's pretty great. So I'm just going to take my, red pen here and just cut through the pi bond because that's the whole point there. Okay, I'm going to draw below here. It really figuratively looks like this, but I think I'm going to draw it like that. So you see, you can just cut, and where you cut, you put those oxygens. Okay, but I don't really like that. I like to put it in linear chain. So 1, 2, 3, 4, 5, 6, 7. So it's a 7-carbon chain. So 1, 2, 3, 4, 5, 6, 7. Okay, and then on 2 there was a ketone. And then on 7, 1, 2, 3, 4, 5, 6, 7, it was an aldehyde. Okay, so it's 2, and that's 7. Okay, and then question, is this regio-selective or stereospecific? And neither. Okay, so regio, no. Stereo, no. Okay, really easy for ozonolysis. Okay, and then last question, I keep saying that, last reaction for alkenes, or chapter 6, is catalytic hydrogenation or catalytic reduction. Okay, so catalytic hydrogenation, and let's be specific of alkenes. Okay, and more specifically, this is going to be known as a reduction. Okay, so remember, reduction is gaining of electrons, so maybe that's important to write. Reduction, if you guys remember, like oil rig, reduction is gaining, so gaining electrons. Okay, gaining electrons. Okay, so let's do an example of that. Okay, and let's just draw down here an example. So let's take, this structure. Okay, and let's subject that to H2. And remember, it could be one of 3 inner transition metals, so platinum or palladium or nickel, either one. You don't need all 3, just one. Okay, and we don't know the mechanism again, but remember, the hydrogen is going to add in this. Don't forget, syn addition. This is key. Everyone forgets this every exam. Okay, this is a common mistake. People forget that this reduction step is syn addition. So you can imagine that the hydrogens can add on the back face at the same time to reduce that unsaturation point, meaning the alkene, and then you pucker those methyl groups to be wedges. So you can see how really you don't just get like a planar to cycloalkane, you get kind of this one stereoisomer. And it's obvious you get them adding on a wedge as well, so it would be meso. But essentially, remember, there is definitely a stereochemical situation going on here. So regio, no. Okay. Stereo, yes. That is chapter 6. All right, everybody take a moment, just let that sit in. If you feel really good about all of that and you followed all and you remembered all those things and I wasn't speaking like, a foreign language, like great, okay? And just, this is your chapter 6 cheat sheet. You guys have a chapter 6 cheat sheet, okay? So that's fun, that's exciting. All right, so do the same thing again, take another sheet of paper, or you guys can be continuous. I think, what do you guys think? Continuous or one sheet of paper? I don't know. New? Yeah, I agree. Okay. Yeah. Okay, so again, hot dog style. Okay. Hot dog style. Hamburger. All anybody cares about is when I'm posting it. I'm gonna try and get this up as soon as I can. That's the goal. How about that? So again, we want 8 boxes. Okay, that was chapter 6. We covered all the chapter 6 stuff. Let's quickly cover the chapter 7 stuff. So this should be really easy because this is really just an extension. And by the way, if you guys are wondering what the list of things we're doing today is, when we finish going over all of these reactions, we're going to do so much synthesis that your head's going to hurt. After that, we're going to do a really good critical thinking question that I think we need to be covering for your test. And we'll probably do a situation of going backwards, of where we have a whole bunch of products and we have to go to the reactants, okay? So yes, we're going to be doing yes, that's what I mean, Abby. We're going to have a reaction diagram question as well, yeah. Okay, so yeah, I think that's pretty much where we're heading, okay? So I know you might think we're just doing review. We are, and then we do a whole bunch of practice. Don't worry, we'll get there. Okay, so here we go. We're on, alkynes now. So this is going to be a reaction in this little box up here. And we're going to do the first one, which is the most, really the most important one for you guys to know, is acetylide addition. Okay, This one is so important because it's going to be useful 100% in your synthesis, at least one of your 2 synthesis problems. You need to know how to do acetylide addition, okay? So let's just do an example of that. So let's take, this terminal benzylic alkyne. So let's just do something like this. Okay, and we're gonna just draw that. And the reagent, remember, was we had 2 steps. So we had, in step 1, we had sodium amide, okay, so it's NaNH2, okay, and it's dissolved in methanol. I mean, excuse me, not methanol, ammonia, okay, and that's just a solvent, an inert solvent. So the main reagent is this base, okay. Remember, amino groups are basic, okay. So for step 2, we had, some sort of haloalkane. So let me just say maybe something like this. X, where X could be chlorine, bromine, iodine, anything like that. So let's just say X equals chlorine, bromine, iodine, etc. Okay. And remember, we rationalize what's going on and why is this just a main reagent? Well, there's a dipole moment towards the halogen, meaning that the carbon that bears it is positive. So we could have a potential, nucleophilic electrophilic reaction happening here. Okay. So the first step we're going to do is draw this NH2, over here. Minus, okay, and essentially that lone pair is going to grab this terminal proton. We talked about why this terminal proton is acidic, and it has to do with the %S character. Okay, so this is the acid-base reaction. Maybe just keep that in the back of your head. %S character is why that proton is acidic. So this base is going to remove that, okay, and we generate the acetylide anion. So that's the main product of step 1, okay. So this is a acetylide anion, and this is also known as a carb anion. Carb anion. So instead of carbocation, this is a carb anion, the anion version of it. Okay, so then in step 2, let's draw that halogen. Okay, so we know it's positive at this part. Remember, partially positive at that point. So that means that the negative is going to come in. Okay, the negative is going to come in and attack there. And then we exceed the octet because remember there's 2 hydrogens already present, 2 hydrogens. So we exceed the octet and we effectively extend this chain 2 more carbons, okay? So we extend it 1 and 2, okay? So now instead of having a 2 carbon, substituent, we have 4 carbons. So the end product is gonna be something that looks like this. Okay, so in our starting material, you might wanna count, we had 1, 2, and now in our end product, we have 1, 2, 3, 4. Okay, we added 2 carbons. So this is the only way we know to add carbons, okay? So everyone listen, if you see on your test and the synthesis problem, which you will, I'm not even gonna lie, you're gonna see that. And if you see that the carbon chain is getting longer, you have to use this reaction at some point in your synthesis. And that's why this is such an important reaction, and we're gonna see that when we do an example, okay? Is this regioselective or stereospecific? No, neither. There's really no stereochemical things or positioning here going on, so no and no. Okay, so acetylide addition, very important. Okay, next reaction is kind of the backwards version, okay, and this is going to be double dehydrohalogenation. Okay, so double dehydrohalogenation is the reaction. Double dehydrohalogenation. Okay, so double dehydrohalogenation, and essentially what we're going to see is we have a, what we call a vicinal haloalkane, meaning where the halogens are 2 carbons removed from each, or 1 carbon removed from each other. So something, let's look at, how about this? Bromine. And I'm going to draw these hydrogens because they're important for the mechanism. Okay, and we're going to subject this to, this is the first time we're going to see something with equivalencies. Okay, so I'm going to draw NaNH2, NH3, okay, step 1, and I'm going to say that's 3 equivalents. Okay, I'm going to draw this in here, and I'm going to draw down here water. Okay, so essentially what's going to happen is, we're going to do the same exact thing we saw, in terms of mechanistic step with the base reacting with all these protons, okay? So let's just try that. So we have, the NH2, and this is the first equivalent. And remember, all equivalents mean is there's 3 moles of this to 1 mole of that, okay? So the first mole, so the first equivalent, is going to remove this first proton, okay? It's going to donate those electrons into this linear form, okay, and then kick off the bromine, okay? So the resulting structure from step 1, or the first equivalent, is going to be something that looks like this, okay? So this is going to be the product of 1 EQ, okay? So that's the first round. And now let's take the second molar quantity of it, okay? And then that's going to remove this proton, donate those electrons in to form the alkyne, and then facilitate the removal of that other halide, okay? So the product of the second equivalent is going to be something 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, okay? So 1, 2, 3, 4, 5, just to make sure. Okay, this is the product of the second equivalent. And then remember, this was the weird part. We, for some reason, have this third equivalent. I don't need to go into why, but it's basically going to grab that proton, okay, generate the acetylide anion, and this is the result of the whole first step, okay? So you get, you know, this weird acetylide anion for some reason, and then that's the product of step 1. And then for step 2, you just clearly have this water reagent hanging around, and, you know, I didn't really explain why in a good way, but it's just going to grab that proton back, and you just synthesized your alkyne. Okay, so just remember, it does this weird, like, extra, removing that final proton for some strange reason and then getting it back. And in terms of the R, that's no. In terms of the S, no. So region-selective, it's not. Stereospecific, no as well. Okay, so this was a way to prepare alkynes. Okay, so let's take a break for a second and think to ourselves, if we have an alkene, okay, and we want to get to maybe this alkyne, what is a reaction that what is my alkene reaction I can do? Okay, so everybody think about that again. If I have to go from an alkene, okay, to an alkyne, I have to clearly do the reaction I just did, right? So what would be the reaction to get from the alkene to this? Halogenation. Great, okay? So you guys can already see how synthesis is going to be important here. If I want to start from an alkene and I want to go to an alkyne of some sort, I have to go through first halogenating it with Br2, okay? And then you have to, I've lost my train of thought. And then you have to do this double dehydrohalogenation reaction, okay? So that's that. Okay, so next one is going to be, we're almost there, we're almost done, I promise, and we'll do practice. Halogenation, okay, of alkynes. Okay, so this is, kind of seen this before, halogenation of alkynes. Okay, so let's do an example of that. So let's just show let's just take this example, okay, and we're going to subject it to Br2, okay, and we're going to show 2 equivalents this time, and let's just pick another inert solvent. So remember, this is DCM, like dichloromethane, because why not? Okay, so essentially this is another concerted mechanism. I'm starting to get lazy on all the details, but basically this nucleophilic pi bond is going to grab that bromine. We're going to exceed the octet, you know, that we've seen this a million times already. And then this, you know, lone pair, another lone pair on here is going to come back and fix that deficiency. So this is a 1, 2, 3, 4, 5 bridged chain 1, 2, 3, 4, 5. That pi bond is between 1, 2, 3, and 4. So 1, 2, 3, and 4. Okay, so now we have this bridged intermediate. Remember, there's no stereochemistry to consider, which is nice because it's sp2, you know. And then we have the bromine that's left over, that anion we generated from that step. Doesn't matter in terms of attacking because they're both secondary. Opening this bridge, okay? So the resulting structure is, and this is the product of 1 equivalent, okay? So then if we do it one more time, because we have 2 equivalents, you can just imagine doing the exact same thing again. So pi bond, grabbing bromine, breaking octet, and then one of these lone pairs coming back to the other side, okay? So the resulting structure again is Br, okay, but already with 2 Brs present. And then remember that anion that we generated from this step is going to come in and attack and break the bridge. Okay, so we get, again, this achiral molecule. Okay, so halogenation of alkynes, we've seen this before, okay? Pretty easy. Okay, next one is going to be hydrohalogenation of alkynes. So we've also seen this before. Okay, example, in terms of regiochemistry and the same thing, stereospecificity, no and no. Okay, so another example, let's just take this example here, and we're going to subject this to, at first, step 1, let's do HBr, that's 1 equivalent, and then step 2, HCl, 1 equivalent. Sorry, I got a FaceTime call. This is good. Okay, so essentially, same exact logic applies that we saw with the first reaction of the day. Pi bond grabs this proton, we generate free bromide. Okay, so the result of that step would be something that looks like 1, 2. Okay, and we formed a carbocation. Okay, this is following Markovnikov's rule, going on this secondary position. And then you have bromide coming in and attacking at that position. Okay, so this is the product of step 1. Okay, so we get this kind of structure. This is the product of 1, okay? And then now you have HCl, so you just do it one more time. So you just take this pi bond, grab that proton, we exceed the octet, we form another intermediate where we have a bromine and then the carbocation is right below it. And then the chloride is just gonna come in, attack, you get a new chiral center. There you go. So that's hydrohalogenation of alkynes. Okay, so consider that. Okay, so we have 3 more reactions left. Okay, so next, this is information overload. It's oxymercuration, demercuration of alkynes. Okay. Okay, oxymercuration, demercuration of alkynes. Okay, we're going to take, again, it's now going to get a lot easier because, again, the mechanisms really stop after there, okay? So we don't, there's a lot to know, but really, you really only have to know half of your mechanisms or half of your main pathways, okay? So don't freak out. So essentially, we're going to do this again, benzylic, alkyne. So, okay. And we're going to subject it to oxymercuration conditions. So HgSO4. H2SO4, and also water, maybe. Okay. So again, how do I know this is kind of oxymercuration? Well, I see mercury. Okay, so that's a big hint. Okay, so, and essentially what it is it's going to form an alcohol. We know what oxymercuration-demercuration does for an alkene. So we're basically just going to add an alcohol to the more substituted position. So essentially what that looks like is, we have 2 carbon chain, okay, and we're just adding an alcohol. Okay, so what was this called? This is called an enol. So alkene, ene, and then alcohol, all. So this is going to be called the enol. And we don't talk about it now, but we're going to draw this, equilibrium arrow, extremely favoring, this other side, and it tautomerizes into something known as the keto. Okay, the keto version. And so this is the keto. So it's enol, the keto tautomerization. I'll write that up here. This is the tautomerization. It's very nice. You don't have to know anything yet. You will in Orgo 2. But for now, just accept it. You go from this enol to the keto. And our logic right now is this is a strong bond, stronger bond. Okay, stronger bond. Okay, so we form ketones when we do oxymercuration-demercuration, okay, of alkynes. Okay, we're good? So remember, equilibrium is favoring this product. That's it for that one. Okay, next reaction. This is going to be hydroboration-oxidation. Hydroboration-oxidation of alkynes. Okay, so let's take maybe this example. So, and we're here. And again, in terms of, let's think about regioselectivity and stereochemistry over here. Okay, so in terms of regiochemistry, yeah, it was really just like, oh, shoot. She wouldn't ask you this because you don't know the mechanism. So I'm not even going to, so we're just going to say not applicable for this question. There is an answer to this, but since we don't know the mechanism, there's no way they would expect you to know if this is regioselective or stereospecific. Okay. So again, this is another 2-parter for hydroboration. This is going to be the SIA. Remember SIA? Okay, so we talked about Survivor and how SIA has her own award. She's awesome. And I think she's awesome. She adopted like an 18-year-old, like pregnant, woman or girl, and, also is now grandma. And like, most people don't adopt like older siblings. So she's a great person, really good person. Yeah, and if anybody cares. Thanks. So this is a 2-step process. So everything is pretty much the same thing as hydroboration conditions for alkenes, except we replaced borane BH3 with this crazy CO1. Okay. So basically what that means is there's a more same exact logic that we saw before. there's a more sterically hindered side and a less sterically hindered side. I think you can see this, and no, alkynes can't rearrange. I just saw that. So essentially, this pi bond is going to grab the boron because, you know, it's deficient, boron the moron, and then this boron hydrogen bond is going to come back and fix that deficiency. Okay, so, oh, I'm sorry, we don't even know the mechanism for this. Okay, so mechanism is not covered. Mechanism not covered, sorry, I'm getting ahead of myself. Mechanism not covered, but you can kind of rationalize how the BSIA2 side is going to line on the sterically unhindered side, and the H is going to be on the more sterically hindered side, and then OH is just going to come and replace it. So essentially, you're forming an enol on the less sterically hindered side. So it would be a 1, 2, 3, 4. So 1, 2, 3, 4, and we would have this enol on the less sterically hindered side. So do you see that? This less sterically hindered side. This is going to tautomerize. This is the keto. Remember, that's an equilibrium arrow, and we're going to prefer the aldehyde. Okay, so aldehyde is at the end of the molecule. Okay, so this is the tautomerization again. So tautomerization. Okay, again, Regis activity and in terms of stereochemistry, again, not applicable. Let's just go with NA for this. Okay. Okay, keep moving. We're almost done. We're on the reductions. You can see the light at the end of the tunnel. Okay, so catalytic reductions. Okay, so this is going to be just catalytic reduction of alkynes. Okay, really easy. So I'm going to do an example. This is actually a really good example to do. So again, we've seen this example a couple times now. And what did I say at the beginning of Orgo 1? If you see benzene pi bonds, do you touch them? Never, 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 never. So really, this is only capable of reducing to that. Okay? And that's it. No mechanism, no regiochemistry, no selectivity, specificity, nothing like that. So that's it. Okay? Easy. Another type of reduction is going to be Lindlar's reduction. Lindlar's, I'm just going to call that red, Lindlar's reduction. Okay? So an example of that would be, let's take this, maybe alkyne. Okay, let's do H2 and let's subject it to Lindlar. Okay, and we're going to get the Z alkene, remember? So 1, 2, and 3. So 1, 2, 3, 4, 5. Okay, so 1, 2, 3, 1, 2, 3. And I'm going to just draw this so you guys know. We're going to draw the line, priority 1, priority 2, priority 1, priority 2. Clearly, this is a Z alkene. Okay? And the last one on the last page, actually, let's just keep it right here. I mean, you guys can do it in another box if you want. I'll just keep it because it's on the same page. The last reaction is going to be sodium ammonia. I don't really have a good name for it. Sodium ammonia reduction. Okay. Okay. So you can imagine the example of that would be, let's take that same example. Why not? And let's just do pure sodium, and it's dissolved in, so that not sign, like degree sign, means pure elemental, and NH3 just is the solvent. So that's an E alkene. So this would be a 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. And that's between 2 and 3. So that's here. And clearly you can see that this, with respect to that line, is an E alkene. Okay. Yes, and this was always Z. Okay. So that is every single reaction you need to know for this test. How do we go? Do you guys like that you have these two sheets now? Good. And no, I'm not uploading a picture of these. Okay. You guys can watch the video on YouTube or get a friend to send it to you. Okay, cool. So let's take a 3-minute break till 4 o'clock, and we're going to spend the next hour really just doing every single problem I can think of. Okay? So this was a chemistry speed. I hope you guys like that. And I'll meet you guys back in like 3 minutes. All right, so we're all back, everybody. I hope you had a good break. And let that digest, and everybody. I'm sure just check the election like I just did. Painfully slow. Okay, so we're gonna do, so I looked at all your responses and thank you guys. There was like 120 of you guys that did that form and so quick. So thank you, that was awesome. And a big, like one of the most popular thing that you guys all picked was not knowing how to do reaction coordinate diagrams or transition states or things like that. So we are gonna go to page, I believe, let me see in the workbook. It would be, page 62 and it's number 10. Okay, so I'm gonna share my screen. Yes, thank you, Hal. I need to remember to do that one. Did Brian just say that? You guys together? Okay, so I gotta write it to myself. Intermolecular closing. Okay, thank you. I gotta remember that. All right, so I'm gonna share my screen just in case you guys don't have it pulled up so you guys can see. I already tried to do this in advance, so where is my Zoom? Here we go. Share. And I'm sure we'll be done within the hour. So if anyone's wondering, we'll probably be done within the hour. Okay. So here we are, if you guys want to see that question as well. You can also see my paper right at the same time. Okay, I just want to make sure. Yeah, good. All right, so we're on 10. So essentially what we're seeing is we have this reaction scheme depicted. So I'm just going to redraw it on my paper. I think that's a good idea for you guys that are taking it, online. So we have, this structure, and we're subjecting it to what looks like, acid-catalyzed ether synthesis. Do we all see that? It's instead of, it looks like almost acid-catalyzed hydration, but instead it looks like acid-catalyzed ether synthesis. So, it looks like we're going to have ethanol. So I'm just going to draw that as ethanol. Okay. And I'm also going to have HCl as my catalyst. Okay. So it's basically acid-catalyzed ether synthesis. So what you want to do for these, like being completely honest, is draw the full mechanism out. This is something you want, if you get this question on your test, which I have a feeling you will, you want to draw the full mechanism out first before even reading any of the questions. Okay. Because all of your questions are just, all of these part A through E are just basically questions about that main mechanism you just drew out. Part A is going to ask you about this one step. B is going to ask you about this other step, et cetera, et cetera, et cetera. Okay. So good rule of thumb, draw the whole mechanism out in its entirety. Okay. So essentially, we know our main reagent is going to be this protonated alcohol. We've been through this mechanism already. Okay. That nucleophilic pi bond is going to grab a proton. Okay. It's going to break those electrons, put it back. I'm doing this fast because I assume you guys are fast at this point. Okay, so we are here now at the secondary position. Okay, so remember this is a 5-membered ring. We have a carbocation. It's that characteristic vinyl substituent. So my guess is I'm going to cut here, break that bond, and put it there. So the resulting, let's count, remember our counting strategy is go counterclockwise from the substituent inwards. So it's 1, 2, 3, 4, 5, 6, 7. Yeah, I like that. Okay, so yeah, okay, so let's basically draw it like this. Okay, so let's call this 5, 6, 4, okay, 3. So look at 3. I pulled electrons away from 3, okay? So that means that it's going to be, we had a methyl group on 3, so that's the methyl that's already present, okay? And what happened is it looks like we took electrons already away from 3. So it's going to be partially positive now, okay? I mean, not partially, fully positive. Okay, and then it looks like the new bond is between 7 and 2, right? So 7 should probably be here, okay? And 2 should probably be here. And then don't forget that on 2, there was another methyl group, okay? So probably something like that. And we're here, essentially, okay? So does everybody kind of see how the ring expansion happened and the numbering? I basically start from the substituent, and I go counterclockwise from the acid of the substituent and through the ring, okay? I'm pulling electrons away from 3. That's why the deficiency that was there. There was already a methyl group on 3, and then basically the new bond is between 7 and 2 also had that extra methyl, okay? That's how I did this. Then essentially, our main reagent now is just ethanol, so I can draw plain ethanol coming in and attacking, okay? So it comes in and attacks, and you basically get this structure. Okay, so keep that proton here. and we're there. Okay, stereochem does not matter. Okay, then the next step, you assume that there's more ethanol left in your solution. Okay, and it's going to come in here and remove that. Okay, so then the resulting structure is now your ether. Okay, so that is the main mechanism. Okay, so stereochemistry doesn't matter because none of these questions are asking you for stereochemistry. Okay, and you'll see that when you read them. Okay, so essentially let's now go through the questions and let's see like how we can answer those. So for part A, it says draw the high energy transition state at the position A. Okay, keep in mind partial bonds are depicted as dashes. So something we want to kind of clarify right now at this point is anything that is, can I draw in here? I don't really know how to use these tools. Oh yeah, okay, cool. Anything at the top, okay, so these tops, the peaks, okay, are called transition states, okay? And I'm gonna draw this symbol. So they get this double, it's an equal signs with a line through it, like kind of like almost like abs. It's like, it's called the double dagger, okay? So any top, like peak, is going to be an intermediate, so they're not real molecules, okay? And anything below that, like in the troughs, let me change colors. Anything in the trough, so here, this is pink, B, C, and D, those are going to be your intermediates. So those would be like a carbocation, okay? So I'll just draw C and plus, okay? So you guys know. So the tops are going to be these fake theoretical constructs known as transition states, which we'll draw in a second. And then what can't you see? What's the situation? Are we good? Can you see it now? Can you guys see my paper? Oh, okay. I'm confused on what's happening. I guess it's good for everybody then, for the most part. Okay, so essentially we're here. So we want to draw what is the transition state at A. So let's look at the first step. Clearly that's the, so each peak, each hill is basically one mechanistic step. So the first hump is going to be this first reaction. So this is corresponding to A, okay? Then this rearrangement is the next hill. And then this is going to be the next hill, okay? So that's like the one after that. And then this is the one after that, okay? So notice how I circled 4 things. Do you guys see that? This is 4 things. 1, 2, 3, 4. Do you see how there are 4 hills? 1, 2, 3, 4. Each hill is one mechanistic step. So that's why you need to draw this full thing out first. Otherwise, you're going to be so lost, all right? So for A, okay, draw the high energy transition state at position A. Okay, so essentially let's draw the, what we want to do is we want to draw this main sigma bond framework, right? So the sigma bond is just all the single bonds, okay? And let's just bring the ethanol here as well. So let's just draw it like this. Okay, so I'm gonna draw like this. I'm gonna draw the hydrogen here. Okay, and I drew it specifically like this for a reason. Okay. So anything that is breaking or forming in terms of bonds in this first step is going to get a dashed line. Okay, so what does a dashed line mean? Well, think about it. A full line is a bond, right? A full line is a bond. But a dashed line we can just use in our minds as a partial bond. It's forming maybe, it's maybe breaking at any position. It's not going to be there forever, essentially. And that's what we're saying with the dashed line. So what's happening? Well, in this step, we know this pi bond is going to go away, right? This pi bond is going to form a carbon-hydrogen bond. And also we knew that this oxygen-hydrogen bond broke. So that's 2 things. A bond is forming, okay? So a bond is forming between these pi electrons, okay? And the hydrogen, okay? And the hydrogen's at the less sterically hindered side. And then also the hydrogen and the oxygen are breaking, okay? So do you see that? So the pi bond is breaking, okay? So that's a bond broken, okay? A bond is forming between the carbon and the hydrogen. And then this bond is also breaking, oxygen and hydrogen. So you have 3 total dashed lines in this transition state, okay? So let's also kind of rationalize, these sometimes we get these partial charges. So we know oxygen is partially positive. So let's leave that partial delta. That's what that means. We knew that from before. But also remember, because we're pulling electrons away from this side, we're getting that carbocation developing, okay? That's right there. So we're also going to put a little partial positive here, all right? And then we put these big brackets around them like this, big brackets, and then we're going to put this double dagger. Okay, that's the transition state, okay? So that's how you would do it, or how I would tell you to do it, okay? So we're talking about this first step, which corresponds to hill A, okay, this big hill over here, okay? So we just did that, okay? So I just put a check mark, okay? So we did A, and I'll put a check mark here too. Okay, we did A, all right? So that's that. There's gonna be more examples of drawing more transition states in a second. So B, okay? So B says, draw the intermediates at position B, C, and D. Okay, so positions B, C, and D are going to be the isolated products of each step. So what directly formed after the first hill or the first step? Well, the first thing was this, you know, vinyl carbocation, I would say. So probably for this one, I would have just, for, here, I'm gonna draw this. This is probably position B, okay? It's the first, you know, bottom trough, or the first product that I got from doing mechanistic steps. And then now I did more mechanistic steps. So what's C? The product, this mechanistic step is probably that one, the rearrangement, the ring expansion. Okay, so the ring expansion was going to be the answer for C. Okay, so this is C. Okay, so we just did, you know, this one. So let me put stamps again. So we did B, we did C. Okay, so that's nice. We did B and we did C. Okay, so what's D? So D is the result of the next step. So now I have addition. Okay, so addition looks like, it's going to be something that looks like this. Okay, so that looks like D. Okay, so check and check. Okay, so do you see that? You have to draw this whole thing out and then rationalize, go slowly, you know, what corresponds to each part in that diagram. Okay, so that was, you know, a good response for B. Okay, so now we're on part C. Okay, so draw the high energy transition state at position E. Okay, so what looks like it's happening at the very end of the reaction? Well, at the very end of the reaction, it looks like it's this final deprotonation step. Okay, so let's kind of practice this one more time. So that's not too bad. So let's draw, you know, the two molecules, the two main molecules that are interacting. So we have this, okay, and I'm gonna draw the proton like that for a reason in a second. Actually, I don't want to do anything there yet. And I want to draw ethanol. Okay. And remember, any bond that is forming / breaking has to get a dashed line. So remember, it's this final deprotonation step where the lone pairs on the oxygen are going to pull the hydrogen, okay, pull the hydrogen away. So essentially that looks like this, okay? And then you're gonna break that current oxygen-hydrogen bond. So that one breaks, okay? Again, this was a partial, not that one, excuse me. Oh yeah, it will become partial positive in the end. So that's why you do that. And then also this was originally partially positive to begin with, okay? So you get a partial positive there, a partial positive there. I don't mean to have that. Again, the big brackets, and then you do the double dagger, okay? So this is another type of transition state, okay? I'm losing people slowly. I see we're down to 85 people. It's okay. So there we are. So we just did E. Okay, so check and check. All right. Oops. I don't know why that went there. Undo. Okay, so that is up to there. So now we're on D. Draw the final products at position F. So we kind of saw that. So the final position is here, okay, at F. And, you know, we generated how many, you know, chiral centers at this position? Guys, put in the chat box. How many chiral centers did we generate from this product? 2, right? So how many major stereoisomers am I expecting? 4, yep. So 2 major stereoisomers. We know the formula, 2 squared, that's 4. So this is a great question for Dr. Peterson to basically have, you know, 4 or maybe even 6 options, and you have to select all the possible, you know, answers to what corresponds to letter F. I totally see that happening. Not too bad. You guys know it's the wedge, wedge, dash, dash, wedge, dash, dash, wedge. You just try all the combos. Not bad. Okay, and then E, sorry. What is the rate determining step of the following reaction? Okay, and it has to be a letter on the diagram. And this is a dead giveaway question. I know it doesn't seem like it, but what does rate determining step? Yeah, it's A. It's clearly A. Rate determining step, all that means is what is the step that takes the longest or has the biggest barrier or the biggest hill? And like, this is just a free, you know, 2 points. Like, it's the one that takes the longest, or the rate determining step is the one that like has the highest energy barrier, which is A, the steepest hill to climb. imagine if you don't understand, in terms of if you're not really good with the reaction kinetics and thermodynamics, my great analogy that I always give to like some thermo students that I'm in a class with is you basically have a giant rock, like you're a Roman and ancient Rome, and you have to like push this huge rock up that hill of A. Is it hard to push it up the barrier for A, that big A barrier, or is it harder to push it over like the C barrier? Clearly it's A. So that's kind of the analogy I use. All right, so this is something that you definitely want to know for your test, and it was the most asked question, one of the most asked questions in the Google form. Okay, so good work on that one. And now we're going to move to synthesis. Okay, so let me kind of get out of here. I'm gonna stay here, and where is the synthesis? Let me stop sharing for a second. We're gonna do synthesis. Okay, so now we're just going to be doing a whole bunch of synthesis questions. This is important. So if you guys really came for this, like I understand why. This is the hardest question on every Orgo exam going forward, and you'll have it in Orgo 2. So actually, Brian and Hal wanted an intermolecular example. And thank you for reminding me. So intermolecular. Okay, so we have this. We have that. So what is intramolecular? Okay, so what intramolecular basically means is that we have this molecule where the nucleophile is already present. Okay, so what we've seen is this plus water, or this and an alcohol underneath. We've seen those two examples. Yes, this is in the workbook. So if you guys care, this is going to be on page 66, letter Y. Okay, page 66, letter Y. Okay. So essentially, like what we've seen up until this point is it's been chlorine and maybe water, and then you know how to draw the Halohydrin, okay? But now in this situation, we already have the hydrate or the alcohol functional group here. So that's why there's an intermolecular, or within the molecule, something else happening once you do this main addition, okay? So essentially, let's just draw, the mechanistic steps of that. The nucleophile grabs the chlorine, we break the bond here, and then we come back and we form this bridge intermediate. So essentially, it looks something like that, okay? And we also get this one. And I'll move it over. Okay, so it could have approached from the front face or the back face. And then now what's going to happen is we don't need water to come in and attack the more substituted side. We already have that kind of in the molecule, okay? So we have this lone pair that can easily attack the more substituted position, just like we've been talking about, and it opens up the ring, okay? Same thing over here. Okay, so let's count the members of the ring. So the oxygen is going to be 1, 2, 3, 4, 5, 6. Okay, so I have oxygen in my ring. Okay, it's a 6-membered ring. Okay, but oxygen is one of the atoms. It's not a carbon. Okay, and let's just number that. So this is 1, 2, 3, 4, 5, 6. And on position 6, it looks like we have a CH2 chlorine group. So CH2 chlorine group. Okay, and we know that this could be the wedge version. Okay, and then over here we get the same product, but dash version. Okay, so that's just an example of an intramolecular ring closing. Okay, so yeah, it's really nothing more difficult than you've already seen. I know it's a weird type of question, but like instead of it being separate, water also, you form basically, you would form like, something like that. Okay, so that's the classic example. And then you would take water, and then the water would attack here and open up the ring. But that's not happening. In this situation, we already have the hydrate in it, okay? I'll do another example. Let me think of one. Let me think. Got it. Okay. This is a favorite. And I feel like if Emily, you're still in here, you're gonna love this one. Okay. 1, 2. Okay. Okay. First thing I want to do is I want to assign RNS to this substituent, this hydroxyl group. Okay. So let's do that. So it would be 1, 2, 3. So what do I think? What's my RNS configuration for this? R. Great. R. So let's just keep that in mind. So what is this going to do? Well, this is my catalyst. It looks like this is acid-catalyzed hydration conditions. So essentially that pi bond is going to grab this proton, okay? We're going to form the secondary carbocation that we've seen. Okay, the more substituted position. Okay, so we're here. And now this oxygen can come in and close the ring. Okay, so we get a 1, 2, 3, 4, 5-membered ring with oxygen in it. So 1, 2, 3, 4, 5. Okay, so on carbon 2, we have a methyl group. Okay, we're going to have to talk about the stereochemistry there in a second. So I'm going to just draw that plain methyl. And then on 5, we also have a methyl group. Okay, so stereochemistry there. So since 5 is sp2, okay, that means we could get wedge or dash. That's why I put a star there. But here we get one specific configuration, and it had to be R. Okay, so to make this R, it's, what do we think? What do I have to make this? A wedge or a dash? Put it in the chat box to make it R. Yep, wedge. Awesome. The answer is wedge. Okay, so we get this staying here, and then you can't say racemic because what we're getting is 2 diastereomers because this stays a wedge, but this one could be either this or this. So you get these 2 geometric isomers. Okay, so that would be the answer to this question. This is a very good question. Okay. Couldn't the RNS configuration change if you switch to a ring? I'm kind of confused on that question. Can you elaborate a little bit more? And Samantha, why does the H on the oxygen go when the oxygen closes the ring? Where does the H go? So the H goes on the less substituted side, Markovnikov's rule, and then the carbocation forms on the more substituted side. Okay, and guys, please keep helping out your friends with those questions if they pop up in there. All right, so that's another example of an intramolecular ring closing, right? And what else was on my list? Synthesis. Okay, so we're gonna go on to page, okay. So we are on page 84 in the student workbook, and we're gonna go through a couple of these synthesis problems, okay? So the big ticket items, okay? So essentially, in synthesis, I like these. They're puzzles. And to be completely honest, I know a lot of you guys are freaking out about this, but the truth is, you guys only know 17 reactions, or 19 reactions so far. Like, there are very few things that we can ask you, like in these synthesis problems, okay? So if you know how to do every single one, A through I, on this sheet, and it like makes logical sense, you're not memorizing it, it makes sense, then you'll be good, because we can't really ask you anything beyond what's on this page, okay? So maybe that kind of gives you some comfort, okay? So essentially, we are here, and we don't know how many steps or what we need to use, but we want to essentially synthesize something that looks like this, okay? This is on page 84, guys, 84. Okay, so we get this, and we get this. So we're there, okay? So essentially, you know, this is a very characteristic thing, and I've been really emphasizing this so much to you guys, and I hope you guys are seeing why. The first thing I want to do in synthesis, so my first rule of thumb is count carbons. Like, that's so important, count carbons. So essentially, I see I have a 1, 2, 3 carbon substituent over here, 1, 2, 3 carbon substituent there, and I extended it a lot to a 1, 2, 3, 4, and then this cyclopentane, okay? So significantly, I added one more carbon and then a whole ring, okay? And then somehow I added bromines. So let's think about something for a second. I need to add carbons, okay? What is the one and only reaction we know to add carbons? Great, you guys are getting it. NaNH2, acetylide, alkyne. Yeah, you guys are figuring it out, okay? So I know I need to get to the alkyne. I'm thinking about that in my head. That's my roadmap. So basically step 2, think about any reaction. Think about like any reaction that you know you need to use, okay? So I know I have to use acetylide. Okay, let's just not even look at the products yet. Let's just play with this and try and get an acetylide. So don't bite more than you can chew. Okay, don't bite off more than you can chew. You just want to do one step at a time. So I'm thinking I need to get to the alkyne. How do I do that? What are we thinking? How can I get to an alkyne from this? BR halogenation. I like that, Abby. Anybody else? I think you meant Roxanne. I think you meant BR2, but yes. Oh, there you go. Br2. Okay, we're thinking that. Good. So yeah, so I know that I can't like do anything right now to get directly to the alkyne, but what I could do is add Br2 or Cl2. Okay, so Br2, DCM maybe, and we're gonna get a structure that looks like this. And you don't have to show stereochemistry and synthesis, okay? So we're just kind of just skeletal structure. So we're there. So we kind of know that this is a good first step. And then, okay, how can I get to the alkyne? I still need to get to that alkyne. What do I need? What do I need? I think I need that double dehydrohalogenation reaction, right? Yeah, there you go, that double dehydrohalogenation rate, NaNH2 again, okay? Yeah, I like that. So basically here is the NaNH2, NH3. Okay, but how many equivalents? This is important. You have to write how many equivalents. What do we think? 3, great. 3 equivalents. There's 3 protons we're dealing with. 1, 2, 3, okay? So the result of that step is the acetylide. So that's between 1, 2, 3, so carbons 2 and 3. So 1, 2, 3. So that's here. Okay, great. I think we're at a good spot now, okay? So now let's think. I know I need to add something to the carbon chain, okay? So what was the reagent? What's that name of that molecule that we have to now use? It starts with an H. Okay, we have to use some sort of haloalkane, right? We need to use a haloalkane, okay? So I know I'm adding the carbon chain by 1 carbon and the cyclopentane ring. So I'm thinking about engineering a structure that looks like this. So that's the 4th carbon that I think, and then maybe, do you see that? Like this is the 4th carbon. I already have 3 carbons, so 1, 2, 3. I need the 4 and the ring, and the only way to do that was to react with the halogen. Remember, the logic there was there's a dipole moment towards the bromine, making a positive on that carbon, okay? So we can see that happening. So basically you can just put that over the arrow line, and the product is going to be something that looks like this. So here's 4 now, and here's your ring. Okay, so we're there. So we're getting closer. We're definitely getting closer. Okay, so then now I need to play with this alkyne, and I want these 2 bromines. Okay, I want these 2 bromines. So what do I think? Those bromines clearly look like they're on opposite faces. Okay, so that's anti-addition. I'm thinking that. So what do you think is my next step? And be careful. Ooh, not HBr. Okay, so everyone's kind of, oh, Samantha, you're right. Everybody else is wrong now. Yes, Jacob, you're right. Okay, so it was a trick, okay? So you have to be very, and this is why I said this, you have to be very good with your alkyne reactions, specifically all the ones involving halogens, okay? So why am I saying that? Because look, we have, let me go up here. We have 2 types. We have hydrohalogenation, okay? And we have halogenation right here. And we essentially showed that we can get these vicinal halogens, 1 carbon removed, and then if we do 1 more round, we get double vicinal halides, okay, 2 of them. But when we try this reaction, we get 2 of them geminal on the same carbon, okay? So there's a big difference. So in this reaction, we get them on 2 separate carbons. But on here, we get them exclusively only on 1 carbon, okay? So that's important for synthesis. You have to know what goes what. So you can't just say like halogenation or hydrohalogenation, because none of that really applies here. So yes, we need to do a reduction. And it doesn't matter, you know, which reduction. I'm just going to pick pure sodium and ammonia, okay? In terms of, I meant by Lindlar's or this one, that's what I meant. So this is a 1, 2, 3, 4. Okay, so 1, 2, 3, 4. Okay, and then your ring. Okay, so that's the cyclohexane ring. The alkene is going to be between 1, 2, and 3 there. Okay, so we're literally 1 step away. We add our bromine to brominate that in GCM, and then you're at your product. Okay, so they're puzzles, okay? And yes, they are very hard, and I'm not even going to like deny that, okay? So this is racemic. They are definitely going to be tough, but for you guys on your test, like, you're not doing this from scratch. Like, you're gonna have some like I feel like it's gonna be fill in the blank. Like, she'll draw partial it, and then she'll be like, what's in box A? What's reagent B? So in a way, I do feel like COVID is coming to your advantage here. But essentially, you still need to know all this, because in Orgo 2, if you're in person, it's definitely gonna come up. Okay. So So this is synthesis. And you do have the knowledge in your head. You just have to go slow and ask yourself the questions. And don't bite off more than you can chew. And also realize that, like, just try something. You really know 17 reactions, and like you can really rule out, like, clearly here I only can really do 9 reactions, okay? And out of, meaning the 9 alkene reactions that I know. And out of those 9, probably half of them don't even apply. So you guys are at a really good advantage. Don't give up, okay? You can just try something and you'll get there, okay? All right, that's what I'm saying. Moving on. Okay, so we're on B, okay? So we're on B, we're gonna try B. So we have something that looks like this. So this is ethylene, okay? Ethylene gas, okay, ethylene. And we're going to do this synthesis problem. We don't know how many steps. And we're gonna have this. Okay, so something I want to give you a very nice hint on. Okay, guys, know this synthesis pathway. It is like the most obvious pathway. I can't tell you, I see this every single year, literally. And to prove that to you, this is my workbook drawn out from last semester. Look at this red and the green. Okay, isn't that exactly what we just did? Alkene, where we halogenate it, we get the haloalkene. We do the double dehydrohalogenate. We get the acetylide anion. Then we do addition. This is a very common thing every semester. So please believe me and know that question. Okay. Cool. So we're here. Okay. First thing, count carbons. Okay. And you're like, crap, I have no idea what I'm doing, right? And I think I dropped a couple of things. They need to have, to finish drawing it. Hydroxyl and hydroxyl. Okay. So we're here. And essentially, I'm like, crap, this looks tough. But I really only know a few things to do. So I count my carbons and I see I have 1, 2. And here I see, oh, wow, I have 1, 2, 3, 4, 5, 6, a lot more. And you're like, where do I even start? Well, I honestly only know one thing. I'm already at the alkyne, and I'm already knowing I have to extend the carbon chain. So that's clearly acetylide addition is going to be my first step. I think we're all clear on that. So the first thing I want to do is I want to show that this is NaNH2, okay, and NH3. All right, so this is going to be the one, NaNH2 dissolved in NH3. Okay, I'm going to say that's one equivalent, okay? And what I'm going to do here is actually make this a little bit more obvious for you. And obviously you wouldn't know this the first time around, but from practice and seeing it, you guys are now going to be pros. So let's call that, again, 1 and 2, and this is in red. I'm going to call this 1 and that 2, okay? And the reason I'm doing that is strategic, okay? And clearly I see I have 2 acidic protons. I have one to the right and one to the left, okay? And specifically, it looks like I'm adding, 2 things, like 2 hydroxyl groups, okay? And we know that that means that there must have been an alkene here probably at some point. Are we all following my logic? There must have been an alkene before this step, okay? I'm thinking there must have been, something like that, right? There must have been an alkene before it to get me here. Okay, so if there was an alkene there, that means that I probably, this is my carbon 1. That's my carbon 2. You're great to think that, Lauren. Good idea. That Abby, great thinking that. Leah, great. That's awesome. So you're clearly thinking ozonolysis. Osmium tetroxide, and we'll get there in a second. But we know that there's the double bond here. So that's why 1, I'm going to call this, and 2 that. And now I see that I have 2 acidic protons. So maybe let's take 1 proton off and add the left side. Let's add this fragment. And then let's take this proton off and add, 3, 4, and 5. Let's add that fragment, okay? So let's try that. So step 1 is going to remove one of these protons, okay? And then you can say this in the same line. Step 2, let's add the right fragment. So let's add 3, let's call this 3, 4, and 5, okay? So 3, 4, and 5. 3, 4, and 5, okay? So that's what I would do there, okay? And then the resulting product of that step would be, okay, 3, 4, 5. Wait, sorry, 1, 2, 3, 4, 5. Gotcha. Okay, so we're here. Okay, so if I want to continue my numbering in the red, 1, 2, 3, 4, 5. Oh, did I do this again? Did I do too many? Oh, yep, my bad. Shakes. They're here. Okay, sorry, they're on 4. Thanks, they're on 4, okay? So we're here. Then we're gonna do another round of this and maybe add this methanol group, this methyl group. So let's do step 1, NaNH2, dissolved in NH3. That's 1 equivalent, okay? And then step 2, we just need to add a methyl group. So that's just 1 carbon. So let's just do CH3Br, okay? Do you see that? That's the, let's call this like maybe carbon A. That's carbon A, okay? So the result of that is going to be this, okay? So now we can do 2 rounds of acetylide addition. We can use 1 equivalent to get rid of this proton, add this carbon chain on the right. We can do another equivalent, remove that acidic proton, then, add to the left. Okay, so now we're good on carbons. We should have a total of 6 carbons. 1, 2, 3, 4, 5, 6. Great, okay, so we're good. So now the rest is pretty much is a little bit more easier. We just have to manipulate the alkyne to get to 2 alcohols, okay? So is there a way with alkynes that you know of that you can form 2 alcohols immediately? No. Yeah, okay, I'm looking for a yes or no. So no, right, yeah. So no, there is no way that I can go directly from this to 2 alcohols. So but I do know that exists for alkenes. So yeah, let's do a reduction step, okay? But this is a situation where the type of reduction really matters, and that's why I'm doing this problem, especially for you guys, okay? So if I were to consider rotating this upwards, okay, if I were to rotate this bond up, okay, and again, you wouldn't know this the first time around, so don't beat yourself up if you didn't get this, okay? So if I were to rotate around that bond, do you guys see how the alcohols have the same stereochemistry? And if I rotated, like, it seems like that's the cis conformation that I'm used to. And I only know one reaction that gets me to this cis conformation, and that's the Z alkene. And that would be H2 and Lindlar. So you have to use Lindlars here, okay? You would get marked off if you pick sodium and pure sodium, metal, and ammonia. And you basically get this this Z alkene. So 1, 2, 3. So it's 1, 2, 3, 4, 5. So we're here. Okay, so this is the Z alkene. That's important. And then finally, we're 1 step away. So we basically just need to do the osmium tetroxide, reaction to get that syndiol that we're used to. Okay. OH. And then the final step to go from here to here is just to rotate back down. You don't even have to write that. You would be fine with just ending right there, okay? So rotating, this bond back down, gets you there, okay? So the stereochemistry, especially with the 2 alcohols, like you guys know, there's only one reaction that has 2 alcohols, right? And you know the different parameters for that. So think in your head, okay, like I know I have to do syndiol somewhere. Okay, well, I only know that happens with an alkene. So an alkene had to have been before that. And if it's an alkene and it's, the syn addition, it probably has to be that Z alkene, right? So there it is, Z alkene. And then, maybe you could have kind of bridged your 2 pathways. Sometimes people start here and some people start there. And then yada, 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 yada. Okay, so that's synthesis for this, okay? And this is how real organic chemists, if you like this stuff, I love this stuff. I actually do it in lab, and I make huge molecules, polymers actually with this. And if you guys like this is like medicinal chemistry. This is all what it's about. Like if you want to make a drug in real life, like they have a target, they have a starting thing, and they're trying to find the most efficient pathway to get there and make it the cheapest, the most potent, and it's such a cool field. I love it. That's you guys. Yeah, it's fun but stressful. I know when you're graded on it, it's stressful. If you guys just take a step back and really just like appreciate, like it's really, really cool. I don't know. I think it's cool. All right, let's keep going. So let's just do another example. Let me pick a hard one. Let's see. Okay, I'm gonna do one more example of what we just did. Okay, so kind of similar. So let's just do. I'm gonna do letter G. Okay, it's on the next page over. So we're here. And we don't know how many steps we have to do. And we basically need to get to, so we have 2 fragments. This is weird. Okay, so let's kind of think about that. So wheels in my head should already be turning, okay? So, oops. So I'm thinking of a couple things. Okay, so I see alkyne, I see alkynes and I see aldehydes. Okay, so I'm immediately thinking like, maybe acid-catalyzed hydration. I'm also thinking maybe it's hydroboration of alkynes. Like maybe I'm also thinking ozonolysis. Like I know ozonolysis might do that. So you see what I'm saying? Like, you just have to like think in your head. You have to really know where you are mentally. Like these sheets, I would literally just like go over these sheets a million times. I'm so happy we took the time to do that, because if you guys can see, I'm a visual test taker. Like I have a photographic memory, so I can see this in my head. I don't know about you guys, but like I know, like, okay, I'm clearly in like the alkyne section. How do I know to make these carbonyls? And I'm like thinking in my head back to this chart, and I'm like, okay, like, you know, maybe that I know there's 3 of them. So that just helps me. So essentially, I'm thinking of all those things. So the first thing I probably want to do is like, I see I have a carbon chain here, 1, 2, 3, 4, and here I have 1, 2, 3, 4, and it's different branching. So this is a huge sign to me that like there is probably some sort of alkene in the middle that we cut, okay? And then there was carbons, you know, going on over here, maybe branch, and then there are probably carbons going on over here, okay? So do you kind of follow that? And then we clearly started with an alkyne. So my guess is I'm probably going to do 2 rounds of acetylide addition, kind of like I saw before, and then get an alkene, and then do ozonolysis. So everybody kind of follow that? Hopefully. Yeah, good. All right, first round, ready? NaNH2, NH3, okay, 1 equivalent. And let's add the left fragment. Let's add, it looks like we have 1 carbon, so let's call this carbon 1, that's carbon 1. And we want to add, let's do it in red. Let's add 1, 2, 3. So we're adding in here, 1, 2, 3, the bromine. So that would be the 1, 2, 3, and number it, please number it, like take the time, it's important. So we have, so now 1, 2, 3. Okay, so we're here on the left side. Let's do 1 more round of this to get to the right side. Okay, so again, you wouldn't have known this the first time around, so don't beat yourself up. But now that you're seeing it, hopefully you'll remember to do it again. Okay, so for step 2, it looks like we already have carbon number, let's just, here. So we'll call it, here, we'll call it 1 again. I'll call this 1 again, why not? I know the numbering is weird. And then we're gonna look like this is 1 again, and we're adding 1, 2, 3, but on 2 we have those 2 extra methyl groups. So let's just do this. So this is 1, 2, 3, and then on 2 you have those 2 extra methyl groups. Okay, so the resulting product from those chemicals would be, you know, this is 1, 2, 3, boom, boom. So we're here. Okay, are we all kind of seeing this coming together? So then, clearly I said earlier, I'm like, oh, what makes sense is probably to have this alkene and then cut it with ozonolysis. So let's get to that alkene, all right? So let's just, it doesn't matter which ones I use, let's just do these 2. Yeah, and you could have used Lindner's here too. You could have, it doesn't matter, okay? So this is a situation where it didn't matter. So 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8. So the alkene is now gonna be between 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, that's here. We have branching here. And then we are 1 step away from our products, and that's just doing ozone, and then, oops, and then 2 is DMS, dimethyl sulfide. Okay, so we cut, and then we see that we have a 1, 2, 3, 4 carbon aldehyde, 1, 2, 3, 4 carbon aldehyde, and then on the right side we had 1, 2, 3, 4 carbon aldehyde, 1, 2, 3, 4 carbon aldehyde for there. Okay, feeling a little bit better? Like, you know something, you know something, okay? So just try it, okay? Just try it, and then just rule things out. This is definitely like a very uncomfortable question, you know? All right, I'm gonna do 1 more example, and we're gonna do just 1 more critical, we'll leave you on critical thinking, and I'm sure you guys are orgo overloaded, so we'll be done. Okay, so, and Dr. Peterson is gonna give you 2 synthesis on the test, I'm pretty sure, 2 synthesis, okay? So that's good. 1 is typically, I hate saying this, but 1 is typically easier than the other, and 1 is typically a little bit harder than the other, okay? So maybe as you're taking it, if you're doing the hard one, you're like, oh, okay, this is probably the hard one. And then when you get to the easier one, you're like, oh, okay, maybe it's easier. Yeah, Lauren, actually great point for the remainder of the people that are in here. I do that all the time. Every time, this is when I was in person, and I did some weird things. Like me and Dr. Peterson would race weird. Like I would be like, Dr. Peterson, watch how fast I can do the synthesis, and like the beginning of like the exam. And this is when I was in person, and we would race each other. But yeah, so point is, is that I think it's actually a good idea to go towards the weird but cute, right? Yeah. But go to, so just go right to the end of the test and do the synthesis. That's what I do, because I think it's the hardest and I can get it over with, and that's it. Yeah, I promise. I guess I'm weird, but like not like unusual, if that makes sense. Yeah, I really get along with Dr. Peterson. She's like a really cool and great person. Hopefully you guys are too. LOL. All right, so here we go. I'm gonna stop talking. Here we go. Yeah, I think that's what it is. I feel a little what's the word? Out of it. Here you go. So we have this characteristic alkene, and we need to extend the carbon chain. That's obvious. So I'm thinking 1, 2, 3, 4 is probably corresponding to 1, 2, 3, 4, right? I know a lot of you guys wish it was Monday. 1, 2, 3, 4 it probably corresponds to 1, 2, 3, 4, and we want to add 5 and the ring. Okay, how am I going to do that? Okay, I know I have to do acetylide addition. What is this huge pathway that you need to know? Like it's unstated that you need to know this essentially. Yes, it's the halogenating first. Great. So let's just try the Cl2 example in DCM. So Cl, so we're there. Okay. Then we know we have to double dehydrohalogenate. Okay, so let's do the NaNH2, NH3, 3 equivalents. Okay, so we get the 1, 2, 3, 4 carbon acetylide. So 1, 2, 3, 4. 1, 2, 3, 4 carbon acetylide. Okay, that's step 1. And then step 2 was, I guess you can either do it in 2 distinct steps or put them together. And then step 2, I'm going to say is this 1 carbon S5 and then that. Okay, so that's carbon 5. All right, so the resulting structure of that is going to be this 5 and then the ring. Okay, so I am really close to my end product. How do I go from the alkyne to the alkane? Someone to say I need a drink. Yeah, me too. But now Felipe's is closed. Rest in peace. H2 and platinum. Any of those transition metals. Platinum, palladium, or nickel. All right. So do you see that? I think that's good with the synthesis. So basically what we're doing is like we're very limited in terms of the beginning, okay? We could only really ask you a few things in the beginning, okay? So just keep practicing these and you'll catch on to the trends. But in terms of the end stuff, this is easy. This is just alkene manipulation. So we're like, oh, let's just do a reduction at the end. Maybe we'll just throw you in ozonolysis at the end. Maybe we'll throw syndiol at the end. Do you see that? Like, it's just kind of like adding the cherry on top. Like, this is the hard part, okay, getting the structure. And then we're like, oh, let's make it a little bit more difficult by just adding like acid-catalyzed hydration. Like, let's add like, ether synthesis, anything like that. Okay, and absolutely, Lauren, great. There are multiple ways you can do synthesis. So yeah, if you thought to do NaNH2 directly, and do 2 equivalents, you could have done NaNH2 dissolved in NH3, and that's 2 equivalents. And that goes right to that, okay? Yeah, totally fine, 100%, totally fine. And, sometimes I remember like when I took it in Orgo 2 or when I did synthesis in Orgo 2 with Peterson, there was one question where like I found a different way than she intended for us to. And she was like, okay, like you got the points. So on the test, if you find something, and you think it works, like, yeah, there you go. Okay, let's do one critical thinking and we'll be done. We have 10 minutes left. All right. And I'm gonna go here. I'm so losing it, guys. What did I want to do? Okay, actually, I wanted to just talk about a few things. I think our time is best spent here. Okay. Share screen. Sure. All right. So you guys see this, hopefully. All right. So let's talk about it. So this is practice exam 3A. And I think this is a really good question. I'm not going to go through each answer, but I just want to talk about how I would answer this. So in box A, that big rectangle at the top, we want to determine which reaction would have the faster rate. So what am I looking for? If I'm looking for faster rate, I'm looking for stable, right? The most stable intermediate or the most stable carbocation, okay? So in 1 or 2, they have the same condition. So they're both going to grab a proton, okay? Both going to grab a proton and form a carbocation. So this is going to form a tertiary carbocation. This one's going to form a secondary carbocation and then have to rearrange to get to the more stable one. So which one is more stable and faster? 1, obviously, right? So 1 would be the answer. Okay, let's look at this one. This is acid-catalyzed hydration conditions. Okay, so it looks like we're going to have the carbocation forming either on the tertiary position or here, the secondary position, but with a nitrogen lone pair attached to it. So this is an electron donating group, right? Are we thinking electron donating? Which stabilizes the carbocation. So does that maybe give me some insight onto why 2 would be the answer here? Yeah? Oops. Great. Okay, so I just want you guys to kind of like ground yourself with this logic. Let me see something, sorry. Here we go. Okay, so then here, clearly we form a tertiary benzylic carbocation or just a plain tertiary. So which one's better, 1 or 2? 1, great. Okay, let's go here. So here we're gonna go through another carbocation intermediate, either secondary position or either secondary position here. But look at the inductive groups. Yep, you guys got it too. Great, okay? I hope you guys can know how to identify electrophiles and nucleophiles, negative, electrophiles, positive. So a lone pair is negative charged, positive, negatively charged, electrophile, et cetera, et cetera, et cetera. What else should we talk about? Anything else? Okay, I've been getting a lot of questions about, some people were emailing me about this question. And this is just an applied question. So this is one of the, so terpenes, I don't know if you guys have heard of terpenes, they're naturally used in your body to make the steroid hormones, so estrogens and testosterones and then things like that. So you actually have these in your body, and it's also kind of, this is cool, it's also used to make weed, like really weird, I don't know, and some tinctures and oils. So yeah, I don't know, it's science, we're allowed to talk about it. And so essentially what you want to do here is we're using this example of you know, these terpenes that are combined, and we're doing an acid-catalyzed hydration reaction. So all I see is 3 pi bonds, and clearly one of these questions is like, which pi bond is going to be used to form that carbocation intermediate? So let's just try it. Like if I use this pi bond, I either have the primary or the secondary. Okay, so fine. If I did that, it would be a secondary allylic carbocation at this position. Okay, secondary allylic. Let's try this pi bond. Okay, if I did it here, it'd be primary, so definitely not. But if I did it here, it would be tertiary allylic. Oh, okay, I see that. This is tertiary allylic. It's definitely better than secondary allylic. Then let's try this one. This one would just be plain tertiary, no resonance. This one would just be plain secondary, no resonance. So does it make sense why I would want to form, let me draw in here, the carbocation here? It's at that position. Yes, this is, it would be here at this, I'm just gonna like kind of draw it. Oh, it's so hard to use with the tool, okay? But this is a tertiary carbocation and it's allylic, okay? Whereas here, this one would be a secondary allylic, okay? So that's why that's kind of explaining the main carbocation rearrangement, at least in part B, okay? And then, you know, you can, A is just drawing the products there. So A would just be like drawing the alcohol add in here, okay? So this isn't hard. I mean, like you guys, it's a different molecule. It looks funky, but you know it. You know how to do this, okay? Let's see if there's anything else I wanted to talk about. And a lot of you guys were also asking for nomenclature practice in the form. Like, I didn't think that was worth going over. Like, I feel like that's kind of just self-explanatory. So just keep practicing your nomenclature. But let's just go backwards real quick. We have 5 minutes left, okay? You 2-hour trekker people that have been in it this long, I'm happy about you guys, and I'm hoping that it really pays off for you. And I hope you guys get the score that you want, because you definitely put in the time, you deserve it. Okay, so we're here. So these are really important, and Dr. Peterson definitely likes to ask these backward questions. They kind of started like about a year ago. So what we're seeing is we have this, you know, racemic product. Okay, so something that clearly, can you guys also see my paper? Just, I keep getting confused with all the screens. Okay, good. So we clearly see we have a hydroxyl group, okay? And we have this methyl group, okay? And what we're doing is we're really, you know, adding alcohols onto the, seems like the less substitute position. That's what hydroboration, you know, tells me, okay? And how is it that I can get, you know, this alcohol in the less substituted position? Well, I definitely can't put the alkene here. So I'm thinking out of all the possibilities, okay, I could put the alkene there. And if I did so, that would form the alcohol all the way over here. So that's definitely not right. So this is not right, okay? But let me try maybe in the middle. So if I tried, you know, here, okay, I tried that, okay, they're both secondary and they both have this bulky group. Like, yeah, you might argue the ring is worse, but remember it's planar. So I don't care. In 3D space, it's really flat. It's actually flat. Oh, sorry. In 3D space, it's actually flat. So you can't, it's not like there's any difference in approaching. They're both secondaries, okay? They're both secondary. So we're definitely on a better track, but this is definitely not the best one. Remember, this is all about attacking at the less sterically hindered, oops, sorry, there's a methyl group here. So, I'm sorry, now that changes the whole thing. Okay, so yes, this is tertiary over here, and this is more sterically hindered, and this is the secondary position, and it's less sterically hindered, okay? But in the sense, you have to have this Dr. Peterson says on the key that it has to be a Z alkene, and it has to be Z for one reason specifically. And if it's Z, you expose, look how exposed this side is, okay? So it's easy for, you know, the alcohol group to align here with the BH3, okay? So this structure is your final structure, or your starting structure, I should say, okay? This alkene, okay? Okay, so let's try B. So for B, we clearly see that we have, you know, alcohols like here, okay? We're doing oxymercuration, okay? And we're adding it to the more substituted, remember, this is Markovnikov addition, right? So let's like kind of try all possible combos, and we could either, you know, maybe try this one, or we could try maybe, let's try with the pi bond one more removed inside. Okay, so the more substitute position, if I did oxymercuration conditions, you just guess and check. That's really the only method to do this. You get the alcohol there. And if I did oxymercuration conditions here, I would get the alcohol here. Okay, so what's my product? Which one does my product show? Clearly this one, right? So this is your starting material. Okay. It's definitely hard to go backwards. That's not what your brain is used to. But there's only like 2 or 3 combos, like by moving the positioning, pretty much for all of these, okay? And C is probably the hardest one. And I mean, I see it. I don't, and hopefully you guys will see it after we do this example, but I'm gonna draw the product down here. Promise, this is the last one we're doing, okay? And essentially what I see is, since it says intermolecular closing, this is definitely hydroxyl, right? Cut, okay? And this must have been the alkene. Do you see that? So I'm thinking that we must have had probably 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. Methyl group coming on here. I'll number that 1, 2, 3, 4, 5, 6. Okay, I'm thinking something like that. On 3, we need to assign absolute configuration. So this one would be, you know, 1, 2, 3. So this is R, right? So we're thinking R. So to make this R, it has to be 1, 2, 3. So it has to be on a wedge, okay? So whatever it is, it has to be on a wedge. And this is on position 3? Yeah, position, wait. Yeah, position 3. So it has to be on a wedge. Gotcha, thanks. Okay, so it has to be on position 3. And then clearly between, it looks like it was acid, what that HCl is, and I showed this example earlier, is there must have been an alkene present, you know, and clearly either, I'm thinking something like this where I could get the tertiary position, okay? And then what happens is that if I get a tertiary carbocation here, that was what formed my ring, the 1, 2, 3, 4, 5 membered ring, okay? So you got it, you guys can do it. Like, it's not so impossible. Like, you know what forms an ether, okay? That would be the alcohol version of acid-catalyzed hydration, okay? And it's just like, I knew to cut here. This was like really obvious to me, okay? All right. And there's one more option. So instead of cutting down there, you could have just maybe cut up here. So there's another possible answer, okay? So the other possible answer could have been the alkene was over there, so something like terminal. And so, whoa, 1, 2, 3, 4, 5. So that would be OH, that. Right? Did you do that right? No, my bad. 1, 2, 3, there's a methyl. That's what it is, okay? So that's the other option, okay? And that was from going the other way, okay? All right, we just hit the 2-hour mark. I hope this helped. I'm gonna post it on YouTube if you guys wanna go back to look at any specific parts. My final parting words for you guys is like, you really do know more than you think you do. I know this is definitely scarier than your last few tests, exam 1 and exam 2, but just realize that you do know something, okay? And everything makes sense, it's logical, okay? So just try and go back to your basics, try and listen to what I'm saying in your heads on the exam, okay? And I think a lot of you guys like this more. So with that, good luck, and I'm excited to see you guys next week and hear all about it. All right, bye guys.